Good morning, everyone. I am Sumit Khalapure, presenting a paper on machine learning techniques for contactless fast body temperature imaging portable device. Uh, Overview. So I'll start with the motivation, how we started, why we started with it, then introduction, the methodology that we used, hardware, software, and the assembly of an entire uh, box that is portable, and then Android application design and the results and conclusion. So motivation behind is like in traditional temperature measurement methods, like there is a lot of time required for multiple temperature reading when there are high density, like a high crowd is coming. Then scan with a thermal gun needs a human involvement and risk the person detecting the temperature. Automated solution are not cost effective if we look at airports, and those are like in their cost is around lakhs and more than that. So our aim is to check the body temperature quickly and to avoid the spread of viral diseases like COVID-19. So solution is, first quickly identify elevated body temperature in high traffic area. Low cost multiple subject measurement should happen, and then identification using photo and video so that we need not stand near to the person that we are detecting the temperature. And this portable device, we called it as a thermomudra, and we have Android app connectivity wirelessly connected to any Android device. It just need to create a hotspot, and connecting to the hotspot will show you on the screen what's the temperature on the face. So this is our hardware where we have Lepton 3.5 IR sensor, and which takes the reading from the IR lights coming, radiations coming from our body. The Pi camera used in the Raspberry Pi takes the optical image. Pixels for both of them is not same, hence we need a calibration to map IR image with the Pi camera, and then whatever face is detected on the Pi camera is mapped to the IR pixels, and IR pixels take from IR pixels we use a Raspberry Pi to process the average of the temperatures around the face, and then it sends to the Android device. So in software face detection, individual frames from the video stream are extracted and converted into the grayscale format. We used a Haar cascade face detection algorithm, and like because of its effectiveness in showing that, and like detected face is shown on the software, and that is that mapping with the IR images is IR image and optical pixels are mapped and shown on the screen. So object tracking is a combination of motion and appearance models are used in the software. So thermomudra assemblies, like we have a 3D printed case in our, like we made in-house 3D printed case. We use that to, like we made it so compact that our all Raspberry Pi, both the optical cameras can fit in that. So that 3D printing in our lab, we used polylactic acid layer, PLA material, and using that we use the snap assembly, so it is easy to assemble, and it's portable. So this is our thermomudra assembly device we have with us. Like in break somebody can test like how it works wirelessly. We did a printed circuit board design for all the connectivity between the Raspberry Pi camera and the mm, IR sensor. So it mainly uses like it uses a power bank also, which has a capacity of 10,000 mAh, and it runs approximately for 6 hours. Like right now also it is turned on so that somebody can check the temperature on the face and see, and it can be charged using a C-type charger. So this is one of the demonstrations. Like uh, in IR image, we are looking at the IR pixels. Those are the radiations coming from the face, and they are very easily distinguishable from the environment. You can see with the yellow patches around the face, and then those patches are averaged out based on what optical image I am taking. So few uh, uh, few measures we need to make sure that the background is plain, because background environment noise also affects the average value of the temperature that we are taking on the face. The results compared to others are like, this work is still in the initial phase where we don't have a, accuracy lesser than 2 degree Fahrenheit, and like it does a multi phase detection, and multi temperature will be shown on the screen simultaneously. We can see that in the time. So conclusion, we have a contactless, lightweight, wirelessly connected device. No internet is required because it creates a hotspot and just gets the data quickly. Pass detection measurement, we saw it is within 2 to 3 seconds. We can see what's the temperature. Device dimension are very like handy. You can see it's in max length is 13.4 centimeter. Device weight is around 342 grams, and operating time per charge is like 6 to 7 hours, which is useful in for all the classroom purposes. Like if somebody's like students are entering, and if we detect a high temperature of a student, we can quickly connect with the student and isolate to avoid all viral infection. And yeah, so we saw that according to market devices, it is 15 to 20 times cost effective. So these are the co-authors with me: Shubham, Jain, uh, his PhD student working along with me, Aditya, Siddharth, and Narasimha. These were the interns with us, and Professor Rajesh Zele is our supervisor. We are working in the electronic circuits.